the chickens. Is everybody up already? Everybody ready to go out? Come on. Time for chickens to go out. Come on. Come on, chicken out. Chicken go. Okay, all you chickens. Now that I've got you all up, let's get to work. We're going to begin today by discussing the topic of plate tectonics, which is a term that you've probably heard of, but let's see if we can extend our knowledge a bit. We're looking down here at the Haleakala volcano on the island of Maui in the Hawaiian Islands. Now, Haleakala sits on the Pacific Plate, which is one of those subdivisions of the Earth that is somewhat, at least, independent of the rest of the planet. It actually moves separately, although certainly it interacts with the other plates. Now, Haleakala doesn't sit at the edge of the Pacific Plate. However, it sits in the interior, over a place called a hotspot, which is a bit like what you'd see with a boiling pot of water. The convection cells in that are kind of like what's going on underneath the volcano here, bringing heated material from the Earth's interior to the surface where it bursts through in a volcano and comes out as lava. Now, the island itself sits upon the outermost layer of the Earth, called the crust. And the crust plus the outermost layer of the next region, referred to as the mantle, form the lithosphere. The lithosphere comprises the solid outer shell of the Earth. It is underlain by a liquid inner mantle known as the asthenosphere. And it is within that liquid mantle that the convection cells are present that transfer heat energy from deep in the Earth to the Earth's surface. Now let's go far to the east of the Hawaiian Islands, to the coast of California. Now, California sits at the edge of continental plates, sitting at the junction between a continental and an oceanic plate, in a place referred to as a convergent boundary, where one plate actually slides beneath the other. This, in fact, is why California is so prone to titanic earthquakes, with that kind of large-scale earth motion going on right beneath it. Now let's travel west again. We are now traveling far west of the Hawaiian Islands to the Mariana Islands, which sit in the western Pacific. They lie adjacent to the Marianas Trench, which is one of the deepest parts of the ocean anywhere on the planet. These islands and the adjacent trench are also the consequence of a convergent plate boundary. In this case, two oceanic plates colliding. So the islands form to the west of the trench in areas where the crust has weakened to the point where the hot interior liquids can again spew out in the form of volcanoes. And that's what we're looking at here. This is actually an old volcano. This is the island of Sarigan, which is an extinct volcano. But just to the north of it is an active volcano. And actually just to the south of it is another active volcano. Now, Another kind of a boundary that we really can't see because it lies beneath the surface of the ocean is that of a divergent plate boundary, like we have in the middle of the Atlantic Ocean, where plates are pulling apart and the Atlantic Ocean is actually growing in size. At the place of the boundary between the plates, an oceanic ridge tends to form because, again, as the crust is weakened by this motion, molten material from deep in the earth comes up and forms what's more or less like a ridge of spewing liquid materials. So let's summarize and add a few additional facts. Planet Earth is in part liquid. It has an innermost region called the core, which the outermost part of is liquid, and the innermost part, primarily nickel and iron, is solid. This is overlain by a mantle, which also is in part liquid in its inner regions, although the outer mantle plus the outermost surface of the Earth, the crust, are solid. These solid layers are called the lithosphere. The deeper layer, the liquid inner mantle, is called the asthenosphere. This is where, by the way, those convection cells I mentioned are present. The energy transferred by these cells is the engine that drives a good deal of the motion of these plates on the Earth, referred to as tectonic plates. Boundaries between plates can be convergent, where we can have subduction zones as one plate rides beneath another. In oceanic regions, where oceanic plates join, you can have the formation of a trench as these plates converge with each other. On the other hand, there are places where the crust is pulling apart at a divergent plate boundary. And this is where oceanic ridges can form as this molten material from deep in the earth comes up along the line of the plate boundary. Also, we can have transform boundaries where plates slide past each other, side to side. Now let's travel back again to the coast of California. We're looking down on Santa Catalina Island here, which is an island off the south coast. It sits in an area which is riddled with cracks in the Earth's crust, these places called faults. And if we look at a U.S. Geological Survey map of this area, you can see just how many fault lines have been mapped through this area. Now, when movement occurs along one of these faults, a seismic wave is generated, which is more or less another way of saying an earthquake is generating. Earthquakes tend to be generated principally along the boundary of tectonic plates, and as we've already seen, coastal California is one of those boundary areas. Now, when an earthquake does occur, the place where it actually happens within the Earth's crust is called the focus of the earthquake, and that can be quite a distance beneath the surface. The area at the surface directly above that is called the epicenter. And so California is the epicenter of many earthquakes. Now, I hope I'm not going to get you all seasick here, but we are again going to bounce back to the other side of the Pacific, to the Mariana Islands. This is the island of Anatahan, which is one of the scariest places I've ever been in my life. When I was there, it was having something on the order of 30 earthquakes a day, because it is an island in that Marianas chain, which is still an active volcano. Now, to be sure, it hadn't erupted historically, so in many thousands of years it hadn't erupted. But in geologic time, that's nothing. This was a young volcano, and it was getting ready to blow its top again. And I'll show you a picture of it later on after it did what it was going to do. But I can make a few interesting points here while looking at this. We can talk about the magnitude of earthquakes. The magnitude of an earthquake is essentially the amplitude of a seismic wave. It is measured by a scale called the Richter scale, which is a numerical scale with a number of about 8 being a gigantic earthquake. But then again, it does depend on how deep the earthquake is centered. If its focus is deep in the Earth's crust, then much of the energy of the earthquake gets dissipated. Whereas if the focus is closer to the surface, then it can generate lots of surface damage. Alright, so now it's again time for a little review and addition of a few further facts. We've seen that the Earth's surface is cracked into places called faults. And we've seen that movement along those faults generates seismic waves. Most of the world's earthquakes do tend to be generated along the boundaries of tectonic plates. The exact location of an earthquake is called its focus, and the location directly above the focus on the surface of the planet is referred to as the epicenter of the earthquake. The amplitude of a seismic wave, the strength of an earthquake, in other words, is measured by a scale called the Richter scale, and by the way, it's measured using an instrument referred to as a seismograph. Very weak earthquakes are in the range of 2, 3, 4. Strong earthquakes, 6, 7, 8. But again, what actually happens at the surface of the Earth depends on where the focus is. Now, one thing we haven't talked about yet are tsunamis. And as we're looking at the island of Surigan on this slide here, when a big earthquake occurs in a place like the Pacific Ocean, and I've actually seen this with my own eyes, the islands, for all intents and purposes, bounce up and down in the ocean, and they generate waves that move away from the islands, and that can then end up hitting the shore of some very distant spot. The energy in those waves gets transferred through the ocean water. In a surface wave, which is kind of like a transverse wave in that it has height, amplitude, and up and down kind of motion, transfers through the ocean water, and as land is again reached, the amplitude of that wave becomes apparent as the wave moves closer and closer to the shore in shallower and shallower water, and the energy gets dissipated at the shoreline. Note also that as a wave approaches the shoreline, its wavelength tends to decrease. In other words, the length of the wave gets shorter, but as that happens, there is a corresponding increase in the amplitude of the wave.